at energy changes in nuclear reaction. Okay, so how does energy change in a nuclear reaction? So remember that the nuclear transformation of any particle involves the destruction of a mass. Okay, for there to be a nuclear transformation or a change in the nuclear energy of a material, there will be a destruction of mass, and that destruction of mass will lead to the what? To the production of what? Energy. So the equation that explains this is known as the Albert Einstein's equation, which is change in E is equal to what? Delta mc squared. So where this is the energy liberated when this mass has been what? Destroyed to a new mass, okay? So this change in m is what we call the mass defect. Yc is what we call the what? The velocity, okay? So this mass defect, which is change in m, can be calculated by summing the mass of the proton and the neutron, which is in the nucleus of the atom, okay, minus the measured mass of the nucleus, that is the actual mass of the nucleus, okay. So then for us to know the energy between that, because remember what is destroyed is the proton and the neutron. So for us to know the energy that is holding those two things together, we can calculate what we call, we can use it to calculate what we call the binding energy, okay. So to calculate this binding energy, the binding energy is calculated by multiplying that mass defect by this constant value. This is the value that was derived from, I don't want us to go into deep how we got this value, okay. It is measured, this is 931.1.4 million electron volts. So binding energy is expressed in million electron volts. So we simply multiply this, multiply the actual mass with this, we have converted it to this, okay. Now this mass defect we are talking about, this mass defect is related to the binding energy holding the proton and the what? And the neutrons together in the nucleus, okay. I repeat again, this mass defect, it is related to the binding energy holding the proton. Remember that the binding energy is that energy that is holding the proton and the neutron in the nucleus before you disintegrate it, okay. So how is it important? How is this mass defect important? If the mass defect is large, the binding energy of that nucleus will also be large, and the more stable the nucleus will be. So this mass defect can be related to the binding energy in terms that if the mass defect is large, the binding energy, which is the energy holding the proton and the neutron together, will also be large, and if it is large, the nucleus will become what? Stable. So we're going to look at one or two calculations to solve under this, just one or two simple calculations that involves binding energy and mass defect. So let's quickly look at this question, okay? So we look at the calculation involving nuclear binding energy and the mass defect, okay? So look at the problem. What is the binding energy for the helium nucleus? Measured, okay, helium nucleus, full stop, okay? So this is the measured mass of the helium nucleus, okay? This is the measured mass of the helium nucleus. So how do we calculate the binding energy of this helium nucleus? So first of all, we are going to get the what? The mass defect. Mass defect is sum of the masses of the proton and neutron minus the measured actual mass. This measured actual mass is this value that was given to you here, which is 4.0028 atomic mass unit, okay? So the mass of the proton will be equal to the proton mass, the mass of proton, okay, times 2. So when you multiply the proton mass times 2, you have this mass, okay? So, and what is this proton mass? From the beginning, the proton mass, the mass of proton, okay, let me give here, the mass of proton is 1.007825, 1.007825 atomic mass unit, okay? While the mass of neutron is equal to 1.007277, 1.007277 atomic mass unit. So if you now multiply, why are we multiplying by 2? Because remember that this is helium. For helium, the proton number is 2. So 2 times this, you have this. The neutron number is also 2. That is 4 minus 2 is neutron number. 4 minus 2 is neutron number. So 2 times neutron mass will give you this. So 2 times this mass you have here That's how we got this. So quickly, we can now calculate the mass defect. Okay, the mass defect will now be sum of these. So sum these two. So 2.014554 plus 2.01733. You sum minus the mass defect. These are the measured mass, which is 4. Okay, recall that this will also be in minus 4.0028. So when you subtract this, the value becomes 0.0291 U. Okay, so this is the mass defect. So the next thing now is to find the binding energy, okay, which is the binding energy. So remember that 1 U is equal to 931.4 million electron volts. Okay, so the binding energy will be equal to multiplying this value, that's the value we have here, that is 0.0291 multiplied by 931.4 million electron volts. So multiply these two values, the binding energy will become this times this. What we're going to have here is 27.1 million electron volts. So this is the binding energy of the nucleus. So this is how to solve problems like this.